All right, guys. So we're on, guys. If you got it, I will not teach. I'm not in the mood to teach. So let me know. Let me focus on my pain and you guys can do you. All right. 4, rational functions. So what is a rational function? Glad you asked. A rational function means that you have a polynomial function in the numerator and in the denominator, okay? Meaning that your variable's in the denominator. And once there's a variable in the denominator, we call that a rational function, okay? The key thing is that it's a polynomial, which means that since it's polynomial, your power can't be negative, right? You can have your power can't be negative, or your power can't be fractional, okay? Because by definition of polynomial, then it's not a polynomial if it's those things. Okay, we're gonna do a quick review of your polynomial parent function, which you guys had part of your math project. Y'all remember our parent function project? That you had to make your own little booklet, your own little slide. And so as we go through this should sound and feel familiar from that information that you gathered. Okay, so to start off with our parent function, we're going to use -2, -1, 0, 1, and 2. And when we plug these values in, we end up with -1/2, -1, and there's a problem here, 0. What happens when you have 1 over 0? It doesn't happen. It is undefined. Do you remember that? Okay. If not, remember it is okay for 0 in the numerator, but it is no-go for 0 in the denominator. Okay. Now we have 1 over 1, which is 1, 1 over 2, which is 1/2. Okay. So these are our primary points for our parent function. Okay. Because it's undefined, what that lets us know when x equals 0, that's a vertical line, right? Pretend that I'm drawing a vertical line. I don't know why I can't trace this line. Okay, at x equals 0, it's undefined. That means that's where we have our asymptote. So at x equals 0, it cannot equal. Okay, does anyone else remember a boundary line for this function? Where is another boundary line for the rational function? On the x-axis at y equals 0, right? Okay, so there's my other boundary line. And now I'm going to plot my points. So I'm at -2.5, -1, -1, +1, +1, +2.5. What these boundary lines mean is that as my function is going, it will never ever, it'll get as close as it can to that, but will it touch? No, it'll never touch. Same thing here. It's going to get as close as it can to that boundary line, but it will never ever touch. Okay, so in there when you wrote what the domain was for your function, so your domain is reading your graph from left to right. What are your x values doing from left to right? So from left to right, our x values start at -infinity, they go to 0. There's something that stops them. So it's like a U, a capital U with no tail. An or is what it means. Or our function exists from 0 to infinity. And the reason why is that because x cannot equal 0. So it's not a continuous situation, right? And the same thing happens from our range. Your range is from bottom to top. So from bottom to top, we start at -infinity. We make our way to 0. Again, we get stop. So, or we go from 0 to +infinity. And the reason being is because our y cannot equal 0. Oh. Okay. So these parts of the function that make it stop, that causes problem, those are our asymptotes, okay? A good way to remember your asymptotes and which is which is OI VUX. Does that ring any bells? Oivux. So oivux, Darren. It's not cute. Okay. So when you have this, how it works is that back to algebra 1, when you have a horizontal line, it has 0 slope and it's y equals a number. Okay. When you have a vertical line, it's undefined slope and it's x equals a number. So when I'm looking for the vertical asymptote, my vertical asymptote is going to be x equals a number. So in this case, my vertical asymptote is at x equals 0. My horizontal asymptote is going to be at y equals 0. Okay. Next, what type of symmetry does the rational function have? It has, well, rotational. We have rotational or origin symmetry. What that means is if you were to take your paper and rotate it 180 degrees, your function would look the same, right? It did not change. Okay? And then we're going to say, is it odd, even, or neither? So what this is saying is that if I took negative x and plugged it into this function, am I going to still get 1 over x? And the answer is going to be no. I'm going to get negative 1 over x, right? So that means that it's not going to be even. But if I made the whole function negative, it's going to be the same thing as if I plugged in a negative x, which makes it odd. Okay, the even odd test that we did with polynomials applies to all functions. It's going to be the same even odd test. Okay. All right, next is one-to-one. To determine whether something is one-to-one by looking at the graph, it has to pass the horizontal line test and the vertical line test. Okay. So if I had a imaginary line that I'm going up and down, up and down, up and down, do I hit more than 1 point at a time? No. So it passes the vertical line test. Horizontal line test. If I have a horizontal line and I'm going left to right, left to right, left to right, left to right, am I hitting more than 1 point at a time? No. So it passes horizontal. So therefore, this function is one-to-one. If it passes the vertical line test and the horizontal line test, then it is a one-to-one function. Okay? To be one-to-one. All right, next, intervals of increase, decreasing, and constant. Are there any intervals where I'm increasing? Meaning, as I read the graph from left to right, as my x values get bigger, my y values also get bigger. No. Reading the graph from left to right, at any point, are there any intervals of decreasing? Yes. I decrease from 0 to negative infinity to 0. I said it backwards. Thank you. And I also decrease from 0 to infinity. And there's no interval of a constant. Okay? All in all, discontinuities. What a discontinuity in just short, we're going to go more in depth with it. Discontinuity. Is there anything that's causing my function to break into parts? Answer is yes. And those types of discontinuities are called asymptotes. So are there discontinuities? Yes, we have asymptotes. What? It's an imaginary boundary line. Say straight or string? That's imaginary. You don't see it. That's the key thing. It never touches. Yeah. So like these are asymptotes. They're invisible though. So when you graph, you're not going to see this dashed line. That makes sense to you. I'm going to. Yeah. Because then it's just a constant function. Like if it's going and then it changes. Oh, okay. I'll give you that. I said as long as it makes sense to you, then yeah. I mean, if that visually makes sense to you, but I'm saying that's not how I would describe it. So therefore, I I think I see it from your perspective. Yeah. All right. This function is also called the reciprocal function. The reason being, if we have f of x equals 1 over x, right? That's our rational function. Its reciprocal function would be g of x, which equals x. And the reason being is, what happens when you take a reciprocal of a number? You're switching your numerator and denominator, right? They're flipping. So like if I look for the reciprocal, I think I spelled that right. Reciprocal. 3 over 4, what would that be? 4/3, right? So that's why this is also called the reciprocal function, because the rational is the reciprocal of the linear. Okay, so depending on some of your textbooks or your instructors, they may say reciprocal function, and it's just another way of saying rational function. Okay. All right. Now we're going to go quickly through transformations. We're not going to dive deep into transformations because that's what all of Algebra 2 was, transforming the parent function. Okay. Ours is supposed to be a brief summary of it. It's supposed to be a brief summary of the transformation. So, really quick, with this function, we have a times f of 1 over x minus c plus d. This is what we call our transformation form. Okay. The reason why it's written in this format is because it's saying that it applies to all functions, right? To all of the rational functions, not just to one, but to all of the rational functions. Okay. Transformation function. Yeah, transformation function, formula, function, whatever you want to call it. All right, each one has a role. So, can someone remember, tell me, what is A? What does A represent normally in a transformation? Your multiply. It's called your what? It's your stretch or compression and your reflection, right? Over the X. Okay. What does C do to a function? It's our horizontal translation. Oh, I forgot a letter there. And we gotta remember that X is what? A liar. Okay, X is lie. That's why they're X's. Okay. All right, D. And D is our what? It's our vertical translation. Is that not what we did pretty much in all of Algebra 2? It was. It's pretty much all we did. Yes. For every function. All right, so. Okay. So what makes it different for rational function is because of our asymptotes, your C and your D also have another rule. Your C is going to be your vertical asymptote. It is your horizontal translation, but it is your vertical asymptote. Does that make sense? Your D is your vertical translation, but it's your horizontal asymptote. Okay? Your C parameter, that's going to be your vertical asymptote. Your D parameter is going to be your horizontal asymptote. Okay? They're the opposite of what they do to the transformation. Your A is your stretch, compression, or reflect. Okay, so now looking at what we have here, shh, be visible. Okay, so here, what is our C? Our X is a liar. -4. What is our D? -5. So therefore, my vertical asymptotes are at -4 and my vertical asymptote is at -4 and my horizontal is at -5. So I'm going to go to -4 And I'm going to go to -5. Okay. So thinking about where our parent function is. So our parent function values that we start off with, it's always going to be 1, 1 and -1, 1. Because I have -4 and -5, in order to make my new function, what am I doing to each one of these functions, each one of these points? Okay, so this tells me that instead of subtracting, if I'm going to use the plotting of the points, I'm going to go left and I'm going to go down. So to find my new points, excuse me, you either use your talk. Don't say no sentence. No sentence. You can go to the college lab and work on your college work. You don't have to sit in here. Remember, I warned you that my patience isn't what it is. Yes, it is. And it's going to stay like this. So we need to go left and down. So I'm going to go left 4, 1, 2, 3, 4, and down 5. 1, 2, 3, 4, 5. So there's my new point. Same thing here. I'm going to go left 4, 1, 2, 3, 4, and down 5. And I'm here. Okay. For the rest of the sketch, you're just going to kind of just follow your boundary lines. Pretend that yours didn't do that. Or mine didn't do that, because hopefully yours are better. Your boundary line is your asymptotes. So there's your function. So after you have this function, what is your domain? What is your domain of this function? So we go from -infinity to -4, and then we break, and then we go -4 to infinity. What is your range of this function? -5, and then we'll break, and we'll go -5 to infinity. Okay, the reason why we have the domain and range that we have is because there's restrictions. What are our restrictions? A vertical asymptote at what? Where's the vertical asymptote at? X equals -4. When you're describing the asymptote, make sure you're putting what the variable it is. And our horizontal asymptote is at y equals -5. Okay, so example number 2, I'm going to help you set it up, but I want you to do it on your own. Okay, so look here, we have 2 minus 1 over x minus 3. Okay, this is the same thing as writing -1 over x minus 3 plus 2. Identify your transformations and draw a sketch of what happened. Because my 2 is positive. Here we go. So we have -1 over x minus 3 plus 2. So what are my transformations? What else? What are the transformations? X is a liar. What else happened? Y'all are missing one transformation. It's my A is no, it's not my 2 that's negative. It's my A. My A is negative. There's a -1 over x minus 3. It said 2 minus 1 over x minus 3. And I said, let me help you and rewrite it for you. And there's a -1 right there. Casper the friendly 1. So A equals -1, which means that once everything's all said and done, what's going to happen to my points? They reflect. Okay. So your C equaled +3, which meant that you went to the right. And your D equaled +2, which means that you went up. So our asymptotes are at 3. So you have your vertical asymptote. Yes. You have your horizontal asymptote. Okay. And the difference here is that your points should actually be here and here because they were reflected. Okay. Yes, they are. It's a misprint. I'm going to talk about it in a second. All right. So our domain, your domain should have been from negative infinity to 3, 3 to infinity. Your range should have been from negative infinity to 2, 2 to infinity. And that's because you had a vertical asymptote at x equals 3 and a horizontal asymptote at y equals 2. Okay? Did we just get stumped on the reflect? Other than that, we were all right. Okay? Remember the negative. Anytime your A is negative, it's going to cause it to reflect. All right? Okay, now we're going to go backwards. Ignore the lines that are already there because when I tried to make your picture bigger, it didn't make the asymptotes bigger. So ignore the lines that are already there. Okay, we're going to draw in our own asymptotes. Your asymptotes are at x equals negative 4. I told you, sorry. And at y equals negative 2. X equals negative 4 and y equals negative 2. I'm assuming this is where Alden meant it starts to go straight. I tried. I see, then I'm back. Okay. All right. I tried to give him something. Here we go. So, because I have my asymptotes, therefore, which parameters of transformation do I have? Which letters do I have? I have my translation pieces, my C and my D. So I know that C equals negative 4 and D equals negative 2. Are we reflected or are we in? We're not reflected. We're in standard position. So therefore, what is the function? F of x equals what? 1 over x plus 4 minus 2. Remember why? Why lie? Just keep what it is. Only the x's lie. What? Yeah, this was a printing error. It didn't shuffle when I made the graph bigger. That's why I said we had to draw it in ourselves. All right, number 4, I want you to identify your asymptotes and write your own function. I'm going to give you 90 seconds. Okay, so someone, where is my vertical asymptote? Negative 6. My vertical asymptote is at negative 6. You can see that's where the split happens and where my function looks like it's approaching. Right? So we have our VA at x equals negative 6. Where's our horizontal asymptote? At 0. So therefore it is no. At y equals 0. Okay? So we had a vertical asymptote at x equals negative 6, and we had a horizontal asymptote at y equals 0. Okay? So therefore, these are our what parameters? This is our C, and this is our D. Okay? What else did you notice about this transformed rational? It's not, it's what? It's reflected. It is reflected, so therefore our A equals a negative 1. So what is our f of x? And that's it. That's it. Good job. Okay. I mean, if you needed to write +0, no one would have known. And that made you better, but okay. All right. Questions, comments, concerns about writing the transform function. Okay. All right. The last part is proper rational form. Do you guys remember, guys, and elementary where you talked about the different types of fractions and you have your proper fraction, your improper, and your mixed number? Yes. Okay. Fraction. Okay. So when you had an improper fraction, what did that mean? There we go. The numerator was bigger than the denominator, right? So when we have if we have an improper rational, what do you think that means? Oh my gosh, thank you for reading. That's our proper. All right, so the proper rational form means that the degree of your numerator is less than the degree of the denominator. It's not no longer just the number, is you have to pay attention to the degree. Okay, so we're proper if my pen, where'd it go? If n degree is less than the numerator is less than the denominator. Okay, when it is not, then we have to perform long division to put it in proper form, which is why unit 3 was about what? Long division. And you already had your test over it, so you all should be pros at it. All right. So we're going to use long division to write each rational function in proper rational form. Okay. So let's start here. Notice, so we have f of x equals 2x squared divided by x plus 3, right? So when I have this, notice that I have the degree here is 2, the degree here is 1, and so therefore n is greater than d. And because of that, we're going to have to do long division. Okay? So setting up my long division, I have x plus 3 divided by 2x squared. Okay, long division, we start off, we divide, multiply, subtract, bring down, right? Divide, multiply, subtract, bring down. So what is 2x squared divided by x? 2x. And then we multiply. 2x times x is 2x squared. 2x times 3 is 6x. Subtract means that I'm changing the signs. And I'm left with negative 6x. And that's it. I mean, you bring down 0 if that makes your heart feels better. But we're left with negative 6x. So now you repeat again. You divide, multiply, subtract, bring down. What is negative 6x divided by x? Negative 6. Now we're going to multiply. Negative 6 times x is negative 6x. Negative 6 times 3 is negative 18. And when you subtract, you're changing the signs. Cancels, and I'm left with 18. 18 is my what? My remainder. And how do we write our remainder? Exactly. So therefore, my quotient is 2x minus 6 plus 18 over x plus 3. And that is your proper rational. Okay, your remainder is always over your divisor. Okay, and again, we already learned how to long divide. So this unit is not about long division. It's about using the long division, okay? All right, so let's look at 6. So 6, we have 3x plus 5 divided by 6 minus x. What is the degree of the numerator? 1. What's the degree of the denominator? 1. So we have n equals d. Dun, 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 dun. It's still not less than. It is equal to. So guess what we'll do? We'll divide. We'll do a little division. Now, when we divide, we're going to rewrite this. So we have negative x plus 6 divided by 3x plus 5. Okay? So that my variable, okay? It's all right. So dividing this, what is 3x divided by negative x? Negative 3. Just negative 3. And then we're going to multiply. Negative 3 times negative x is positive 3x. Negative 3 times 6 is negative 18. We subtract. And we're left with a remainder of 13. Isn't it 23? Yeah. So here's my remainder. So we have negative 3 plus 23 over 6 minus x. Yes. All right, you're due now tomorrow. We'll be to do the